Hello, I'm Robert, and this time I'm going to talk about how NASA have never issued any asteroid alert, and how the most likely future warning is something very harmless. And I'm doing this for Doomsday Debunked, where we debunk stories like this that scare people. So, first of all, so these are all the fake news stories. You can see I've done a video about this before. Asteroid warning. US Defense Secretary warns devastating impact could be tomorrow. And this is just made up stuff. NASA asteroid warning. This colossal asteroid will skim Earth. And these are normally by the likes of the Daily Express or something. It's just not true. It's just made up. Google News is spammed by loads of fake asteroid warnings. And the programmers there don't seem to have even noticed, or they're not bothered about it. And now this is my non-techie interface to the techie NASA tables. It's got if you look at the techie numbers, there's all these zeros in it. The zeros mean no hazard, and they don't fully explain it very easily. It's a couple of clicks away and quite hidden and difficult to understand, but that's what it means. As of today, as of writing this, there are no asteroid or comet warnings, and there never have been. All those are fake. And that's the most likely thing that we will get. This is an actual simulation of they simulate an impact into an ocean. So I'm going to talk a little bit about we actually have had some impacts by asteroids in the past. People have died of asteroid impacts. In small numbers of people have died of them. So it's not nothing, but the ones that they talk about is just fake news, and we already are tracking most of them. And they never run any asteroid warnings on the Center for Near Earth Object Studies because there haven't been any. So let's look at what has actually happened. Let's scroll down. First of all, we have been hit by even one as big as 1 kilometer in diameter. That happened 700,000 years ago, and that's the most recent, kind of biggish one. And at that size, then it wouldn't actually it wouldn't have a very noticeable if you're on the other side of the world, in Europe or something. You'd hardly notice. You'd get the weather would be a little bit cooler for one season than you expect for that time of year, because there's a little bit more dust in the atmosphere which blocks out the sun. And the Homo erectus, which was before Neanderthals and before Homo sapiens, before us, tool-using hominid, then it would have seen it. And it survived it, of course. This is the most recent one. That's the Chelyabinsk, and it was a bright light in the sky, and this is the shock wave. It's just like if you had a very, very fast supersonic jet and you get the sonic boom. You get a kind of sonic boom from the asteroid, and then the boom is so big that it can blow out windows, and this is the glass that was shattered, and that's the most likely effect, that the only effect, and some people were badly injured by that, by the flying glass. So most likely you get a warning, and then they would get a warning. These people do not, and they talk about how the governments. People keep on going and saying, "Oh, there really is going to be an impact, there really is," and the government is hiding it. Governments do not hide disasters, except in movies. There isn't a single example. It's very fictional. In movies, it's a great way of building up some tension by having the government hide what is going on. And then you have this astronomer who's seen an approaching asteroid, and then he tries to tell the government to say, "Oh yes, we know about that now, come away to our little secret base here, we are going to escape Earth," or something. It doesn't work like that. The Center for Near Earth Object Studies was actually set up by the US government, and they are held accountable to the US Congress. They are being paid, just as weather forecasters are paid, to find these asteroids. And they'd be out of their job, and they want to protect people as well. That's the very reason that they're searching for asteroids, is to be able to warn us and protect us. And if there ever is a real asteroid warning, then it would just be like when you have the hurricane warning, and you have to have these maps, and they say, get out of this area. And it's them, this is an example of hurricane warning. And they'll be telling people in that area, get out, move out, move out. And the people in those areas, and some of the really stupid people, will have a storm party and they'll refuse to move. And that's the sort of thing that could happen with an asteroid warning. They are going to be the ones trying to get you to move. But they're really, really rare. Like if the Egyptians had developed asteroid, they weren't very far off modern science, just a few discoveries away. If they had developed telescopes and rockets, their rockets would just be sitting idle, getting rusty and having been maintained for thousands of years, and they wouldn't have had to deflect anything. However, there have been a few small things, very small. So now let's look at if I bring up, scroll up, and yes, there was I said there's a hamlet was destroyed by a meteorite in Santa Ana in Mexico, and 8 people were killed, 28 injured. That's in May 1946. So people do get killed by these things, but it's very, very rare. These are some actual impacts, but they're from a long time ago. So an iron meteorite is much stronger than other kinds of meteorites. But this one is, this isn't an iron meteorite. I should change the description and make it a bit clearer. This was an ordinary chondrite meteorite, but the air is very thin, and high up in Peru. And so that's 3,800 meters. So you also get, sometimes when the air is very thin, and a very small meteorite can actually create a tiny crater, and it goes through the atmosphere. And this crater was 13 meters across and about 4.5 meters deep. And one villager was riding a bicycle and he fell down and was dizzy of all the bright things flying past and all confused. That was the only casualty there. He wasn't hurt, he just got a bit dizzy. His eardrums weren't ruptured. And now this is from about 1600 BC, and this is an iron meteorite. It may be a bit smaller than that, I just did a calculation there. That's where it is in Estonia. That's what it looks like. And there's not much to show for it now, but at the time it could have caused a firestorm that went out for about 6 kilometers. So that is something that it would be quite hazardous if you were around. We definitely want to be warned about this. So the thing to bear in mind is that you can be killed by lightning and you can be killed by a hailstone. Lightning is very rare. Hailstone is much rarer still. The last time anyone was killed by a hailstone in the United States was the year 2000. Last time anyone was killed by a meteorite, it's not known. There's not in the 20th century, and it doesn't seem to have happened in the 19th century in the United States. There's one fake account, which is known to be fake from the 19th century. So they're pretty rare. But we do have these. Say there was people killed in Mexico in 1947. There were 3 reindeer herders were killed in 1908 in Siberia. So, but I mean, compared with being hit by a car in a traffic accident, or it's not comparable. It's not a personal risk, but it is worth doing it for the world as a whole. And so that's one. And there's another one, Henby craters, that's about and the Haviland impact crater in the United States from 20,000 years ago. That's measuring it, just quite a small crater by an iron meteorite. And the Maha crater in Asia, about 300 meters in diameter. That's a picture of that. And there must have been many more. But then if you go and look at the next 8,000 years, and we are surely going to have many more craters like that. So I've got this map up here somewhere. Just try and find it. Oh, there we go. So, if you look at the entire world, and since these can hit randomly anywhere, most of the world is ocean. So the most likely, if you think about what's going to happen next, they're now tracking lots of them, but they wouldn't necessarily find all of them. So it is possible for one of these small ones to hit without being noticed in advance, although they're getting much better at it. But hopefully they have been noticed a few very small ones in advance. The most likely place for this to hit is in the ocean. And if it's small enough, like the Tunguska one, or the Chelyabinsk one. And there may have been once, even in the past century, it hit in the ocean and nobody noticed, before we had all these sensors set up to detect them. One hit in the Bering Sea a few years back, and that was only noticed long after the event, when I look at it's not ultrasound, the other thing, subsonic, very very low frequency sounds they detect, and they detect them through those, and the sensors they set up try and monitor nuclear explosions, and they don't find any nuclear explosions, but they keep noticing these fireballs from the impact, and then the bigger ones over the Bering Sea a few years back. Well, I've got that down here somewhere. Anyway, so in the next 1,000 years, you would expect 30 to hit the Pacific. In the next, say, 10,000 years, it could be 8,000, depends how often they happen, long enough for 100 of them to hit. You'd expect 30 to hit the Pacific, 20 to hit the Atlantic, 14 to hit the Indian Ocean, 4 to hit the Southern Ocean, 3 hit the Arctic Ocean, so that's 71 would hit the oceans. And then 3 would hit Antarctica, 3 hit polar ice, 2 hit the Sahara Desert, 1 hits either the Australian or Arabian Gobi Desert. And then so you're only left with 20 after all that. 9 would hit forests, 7 grassland, 3 would hit agricultural land used for crops, and then you'd have 1 in the next 10,000 years could hit an urban or semi-urban area. And these are all roughly equal, and then very remote chance for the urban area. Those are the urban, I think the urban areas are shown in red there. Yes, the urban areas are shown in red. Very, very small part of the surface, only 1% of the total surface. And there it is as one of these plot things. So by far, and that's a further, I think that's a further breakdown. That's, yes, this is the, that's just a further breakdown of it. And so this is the most likely thing, splosh in the Pacific. And these things aren't big enough to cause a tsunami at all, not unless they're really big. They have to be hundreds of meters to cause a tsunami, even an ordinary tsunami. The smallest ones, you see, the thing is that if you've got even like a 50-meter one and it hits the ocean, then it creates a great big splosh like this, and it creates a cavity, and the cavity then sort of boils, and then immediately the water rushes in to fill that cavity, and that undoes the effect of any big wave that would go out. And so you get a great big splash. It's like a plop into a puddle, and you get a great big splash goes up, the curtain then falls down, and then they're very low frequency waves, low wavelength, short wavelength waves, and this means they dissipate very quickly, like a splash in a puddle, and they just fade away, and before they got anywhere near any land, and they'd just be a big wave that would just break if they did come ashore. But they just don't travel very far, because in order for the wave to travel without just diminishing very quickly, then the wave has to be comparable, it has to be actually bigger than the depth of the ocean. So unless it's a very shallow ocean, and that's significantly bigger, I think it's 30, 20, I forgot the figure there. For a tsunami, it's typically about 100 kilometers. Yes, wavelengths typically more than 20 times the depth of the sea. So if the sea is a kilometer deep, then the wavelength has to be 20 kilometers. And a 50-meter diameter asteroid just can't create a tsunami. Even 100 meters once, then it's not going to create a proper tsunami. The worst you can get, even for like say 200 meters diameter impact, they will create a somewhat bigger hole in the sea than the size of the actual impactor. But that is still only big for very, very feeble tsunami, which is more like a storm surge, because and it would just go up quite gently and then come down again, and it would be it would be quite short-lived, rather feeble. It's not like the tsunamis, which are typically 100 kilometers wavelength, and that means that as the wave comes in, it keeps coming in, and that's what makes them so destructive. Whereas these just create a wave, and that's not so destructive at all as a tsunami, a normal wave, or maybe quite a large wave. So you don't need to worry about tsunamis unless it's really big. And now, yeah, that's just a fireball seen from the ISS. We get lots of those. And these are the government sensors. That is Chelyabinsk, and that's the Bering Sea one that I mentioned. So Chelyabinsk, a tiny little asteroid, and there's the Bering Sea. And they spotted it, and afterwards, they found these photographs of it seen by satellites. And if you look very closely there, there's it's seen there as well. Quite hard to spot. And there we are. That's the kind of train from it, I think. And it wasn't hidden. It's just that it wasn't. Yeah, infrasound. That's the word. And they routinely they didn't release their fireball observations straight away. They do it later. They just do that. It's just kind of security thing. It wasn't anything to it trying to hide this. And it's released from time to time, and NASA go back through it and they make the fireball stable. And nobody seemed to have noticed it because it happened above a thick cloud. So there's probably been, and it's probably in the past, nowadays we would at least spot it after the event if it landed in the ocean. But there's probably been many of them in the ocean for the few that we've got on the land that we know about. So yeah, this is about how if there's a 1 kilometer asteroid coming our way, then, well, we expect it. They only 1 kilometer ones, likely hundreds of thousands of years before the next 1 kilometer one. But if one was, and of there are 901 as of speaking just now, unless they just covered another one in the last day or so, then there's 901 of the 1 kilometer asteroids being found so far, and only one of those. All of them have been removed completely from the risk table, except for just one, which has a chance in 2,880, but it's expected to miss. So of the remaining 50 or so of them that are left to find, it's very unlikely that any of them have any chance of hitting Earth in the next 200 years. And in the very remote chances, sometime in the next century or so, then we expect, in order to be hidden for this long, because they've been looking for the last decade and haven't seen it, it's probably hiding behind the sun. And that means it's got almost exactly the same orbit as Earth. And it would take only, and once it peaks beyond the sun, then all of our telescopes that are looking will immediately spot it. Whenever they next would look that day, within a few days, then Atlas would spot it, and Pan-STARRS within a week or two or something. And because they do these different surface of the entire sky, Atlas does it very quickly, Pan-STARRS more slowly. And just as soon as they're pointed that way, they spot it. And then it would take ages to come around to Earth if it's been hiding behind the sun for an entire decade. And that's the most likely place. And if typically we'd expect a 1 kilometer asteroid, it would be about a year before, and this was just using the Atlas simulation. They found nearly all of them are detected a year beforehand, just using those telescopes. And given all the other ones, I think we can't absolutely guarantee this, at least unless there's been a recent paper that's proven we can. I haven't, but it's really incredibly unlikely that one approaches us with less than a year of warning. And it's the same for a comet. Comet will be a year, 2 years longer than that, most likely. But most likely be several years warning if it's as big as if it was a 10 kilometer one, and 1 kilometer one, again several years, very likely. But comets are very rare these days. They typically pass by at further than the sun, and we see them so often because they have these huge, easy to spot tails, which you can see right across the solar system. The tail can be as big as the sun. The coma can be as big as the sun for a comet, and the tail as well on top of that. And very flimsy, but reflects a lot of light, and that's why we see it so easily. But they're very far away, typically, and really the risk is infinitesimal almost for comets, long-period comets. And now, these are the ones that were actually particularly in advance. This is one of the first. So when I say that NASA have issued no asteroid warnings, they have predicted some very tiny asteroids in advance, but they're too small to be a warning. They're just fireballs. So remember I showed you that fireball table. Where is it? This fireball table. So this is the many of these every year, of these just bright fireballs, and the larger ones would be as bright as the moon, and then for people nearby that one was as bright as the sun, if you were close enough. People actually got sunburned by it. And these are as bright as the moon, but they are not. People say, oh, this was as much yield as a nuclear weapon. Well, in a way, yes, but in a way, no. Yes, because they are as bright and as much energy as a nuclear weapon, but no, because they typically burn up high up in the atmosphere, far beyond any possibility of harming people, and there's no radioactivity. So all these comparisons with a nuclear weapon are very misleading. They're not harmful in the way a nuclear weapon is. You can have a megaton, one of these, or kilotons and megatons, and it's still not going to be big deal unless you're very close. I can't remember what this was in Chelyabinsk. What is it in kilotons? Let's do a little search since I brought that up. I tried not to digress, but I sometimes do. Let's just quickly look that up. Have a little bit of break. 500 kiloton, assuming Wikipedia got it right, which I would have to check the site. Then you talk about half a megaton, I think. Yes, about half a megaton. 33 times. So let's check their site to see if they got it right. Space.com. You should always check Wikipedia. Yes, 400 to 500 kilotons. Most part, and Tunguska was about 3 to 5 megatons. So, so when they say that it's like a nuclear weapon, then it doesn't mean that there was no radioactivity. The only real danger was a bit of sunburn and the flying glass from the broken windows. So that's a bit of misleading comparison when they talk about them, compare them to nuclear weapons. So that's so these ones were predicted. These are I was talking about the predicted asteroids, and so a few others have been predicted. There's another one. This was predicted, and then they actually saw it in a plane. And then there was another one that was predicted, and then they saw it. They've actually found it on the ground in that case. And this one was that the one that was predicted and then seen. Here we are. That's predicted and was seen with webcams. You can actually watch this. So it's basically just a fireball. They've got to the point where they actually are predicting some of the fireballs. They're predicting this fireball, completely harmless fireball. And it's very small, but they predicted it. So that doesn't count as an asteroid warning. And these are all the people that saw it. Very bright. See, all these people from a vast area, they saw this. So you can see it very bright over a vast area. Talk about impact craters. And so now what have I not talked about? These are the telescopes. So they would build this large synoptic survey telescope, which find 80% of the ones above 140 meters within a decade. And that's going to be built, I think, 2021 or something like that. Very big telescope. And this can see 4 times further away than any of our existing telescopes. It's in the southern hemisphere, so it plugs up a bit of a gap that most of our telescopes are in the northern hemisphere, even if they're just north of the equator. There's a little bit of a hole at the South Pole. It doesn't mean asteroids that would be difficult to detect, but then in their orbits eventually, no asteroid can't stay south of Earth throughout its entire orbit. At least a part of its orbit has to go north of the Sun if it starts off south. So we do see them, but this will help us to spot more of the asteroids. And in its first week of operation, it should find vast numbers of new asteroids, small asteroids. So, what else? And yes, so now this is a new development, synthetic synthetic tracking. And what they do is they take all these photographs, and in each individual frame the asteroid is too small to see, too faint. And so there's a big advantage in spotting. If you can see them much easier in infrared for the very dark asteroids, because even if they're very dark, they actually radiate very well in infrared. Infrared gets blocked out by our atmosphere, so at least some of it, not all of it, but some of it. And if you can put our telescopes above the Earth's atmosphere, then a small telescope can outperform a big one on the ground. And just have tiny little infrared telescopes in space, and then have several of them, then they also can outperform because they can point closer to the sun. And they can also outperform because you can put them in a different orbit between Earth and Venus, for instance, just outside of Venus's orbit. You could have 8 of them there looking outwards, and then we'd find vast numbers of the tiny ones very quickly. Within a decade, they'd find lots of the small ones that would be missed by other telescopes. And there's another way of doing it. If you were to put one in between Earth and the Sun, in a kind of guard position, and the L1, Earth-Sun L1 position, then looking outwards, looking at a kind of cone, so you have a mirror that rapidly spins around, and a secondary mirror in the main mirror, and then using that, you can rapidly scan in a few minutes an entire kind of conical section like that guarding the Earth, like that. You scan the whole thing, and then any asteroid that was coming towards Earth would pass through that little guardrail that you've generated, optical guardrail, and you'd have 3 or 4 detections, and so you'd be able to get apart from that. And then, once you've found it, you can alert other people and say, look, we've found an asteroid going that way. In fact, they would have 2 of these things. One would do the guarding, the other one would take a photograph of the thing that the other one had noticed and help with the tracking and then the telescopes on the ground. This could give us 2 days warning, which is enough time to evacuate a city. So with that plus ground telescopes, we could have very efficient warning of even the small ones. And I mean, like, a billionaire could get this out-of-pocket change, could buy this system. It's $50 million, I think it is. So if there's any billionaires watching this, do consider maybe buying this and to help protect the Earth. Or and again, governments of other countries, or so even a small country. It doesn't have to be the US. Although I understand that I think if we get a keen senator in the US who really were to take this up. So if anybody watching this is a senator or a congressman in the United States and wants to take this up as a hobby, as something that interests you, then it needs to be a ring-fenced budget separate from NASA, because NASA, they do not, they have to evaluate things by their scientific merit, and they'll just keep rejecting something like this because it's not got the science merit of finding out about asteroids, that the things that they're tasked with finding, and that's why NeoCam keeps getting rejected. So and that shows how you, the result of stacking many images, you see it. So that's one way, and there are various other ways. So they're talking about why we want to do that and various ideas about it. And this is NeoCam, which has been rejected twice so far. They tried to get it through the NASA processes, but they just rejected because NASA can't accept a mission like this unless there's nothing else competing that's better for science merits. And for instance, last time, I think it was it competing with them? They approved a helicopter to go to Titan and fly around in the Titan atmosphere. And how can something like this compete with that, for scientific merit? So I'm not sure if that was the one that competed with it, but they definitely competed with the one to go to Psyche, to go and look at an iron meteorite, very large iron asteroid close up. And so they're just going to keep, they can't do it. So we have these telescopes on the ground, and they're not covered by the NASA budget, and so they spend hundreds of millions on those, but they can't seem to spend 50 millions on a space telescope, because that falls onto NASA, and NASA just keeps rejecting them because it's required to reject them by its own policies. So it's a very silly bureaucratic hole that the space telescopes fall into. And I think we should plug that hole, and we should have a little ring-fence budget. Don't take away from NASA. Just say we put $100 million a year, say, or even less than that, and we use that for a space telescope. Even just a one-off thing of $100 million would do it probably. Compared with amount you spend on defence. And as I said in one of my other videos, then if we had the amount that we spend on defence against each other, an extraterrestrial from a just somewhat more advanced civilization, just a century or two ahead of us, and most likely we ever meet extraterrestrials, they'd very unlikely evolve at the same time as us. So if we ever meet a real extraterrestrial, probably not in real life, but by communicating a few hundred light years or 1,000 light years away, or more likely maybe tens or hundreds of thousands of light years away, and we get a signal from them. But when eventually they talk to us and we talk back, and they'll look at us and think, oh, that's what we were like, sort of 500,000 years ago, when we first started becoming a civilization, and we just spent all our money on defending against each other, and we did very little to protect ourselves from space. And we will seem incredibly primitive to an extraterrestrial, I think. That we're just not spending anything on this. But we are doing a fair bit, but nothing like what we spend on defending against each other. Not even a tiny fraction. Even the smallest country, North Korea could easily pay for that, or I don't know, some very Botswana, or some very small country could easily pay for that if they decide it was a priority instead of building a new road or something. I'm not saying they should, but it's for the world as a whole. Given our 7 billion people, I really don't understand why we don't have one of these tiny little space telescopes. But if we don't do that, then don't worry. We have these. At least it's very low personal risk. Personal risk is minute, far less than lightning or hailstones. It only makes sense because we've got 7 billion people, and it's worth doing it for the 7 billion people. And there's a tiny chance that this could happen again. That we have something like Hamlet in Mexico, another 8 people die, and even for that, I think we should have this. And it is there just in case we get a bigger one. And but meanwhile, those are all some of the telescopes that are keeping us safe. This is the radar telescope, the accelerator radar telescope. That's very precise tracking when it comes very close to Earth. So those are some of the telescopes that help keep you safe from asteroids. And over the next couple of decades, we could just do it much more quickly with the Space Telescope in a decade or so. But by 2030 and then 2040, when we get 2040, then we found by 2030, then the LSST alone will have found most of the ones of 140 meters and larger, and we'll be finding a lot of the smaller ones as well. And by get to say 2040, then surely we'll have some space telescopes in sometime in the next couple of decades as well. So the cost of them going down, and someone will do it at some point. And so I think this may be the last decade when there's really been a chance of even a small asteroid. 2020s might be the last decade when there's a chance of a small asteroid hitting without being detected at least a couple of days in advance, like a hurricane. And unlike a hurricane, we can. So let's just. This hasn't been so long. Let's look at deflecting. Methods of deflecting asteroids. It's now 35 minutes, so I'll just do a few minutes on asteroid deflection. So the gentlest way to do it is with white paint. So I've got a video about it there. Not sure if I'll play the video. Or you can cover it with a blanket. And the Apophis keeps coming up in the news. And this, if you could cover it with just a few tens of square, it's actually, I think they a bit hundreds of square meters. Sorry, 40 by 40 meter there. And then just 40 by 40 metre was for one of the mitigations they had there. A patch with the lightweight reflective materials. I thought it was larger. I got confused at some point. Maybe I thought it meant feet as metres. It's for 40 by 40 metres. That's quite small. And that is like a solar sail material. It would be very thin, just micrometers thin material. You just put that on the surface of a boffice, and that would be enough to change a miss to a hit. And the reason is that, and so if they did as late as 2018, because it was a close flyby in 2029, and so they could easily, if it was going to hit in 2036, we now know it's going to miss. So, and the same thing, if we found when it flybys in 2029, it's going to miss hit in 2060, we could use a similar method to deflect it, because when it goes very close to Earth, it goes to what's called gravitational keyhole, where even just shifting it by 100 meters or less can change it from a hit to a miss next time around. So that's the easiest way to deflect them. But that only happens if it does flybys of Earth first. And the gravitational keyholes are only there for very close flybys. So the sensationalist press seems to suggest, to give the idea that you could zoom them all over like the Star Trek impulse drive and sort of portals in space. That's just made up fiction. They can't zip around like that, but if they travel very close to Earth, it can be deflected. So then, and you have kinetic impact, and so the mission we have actually got the DART mission is going to be hitting the moon, and it just hit a moon. If you can hit the impact, just hit it going by tens of centimeters, it's about the speed of a snail moves. That much motion can easily turn into a miss a decade later. And the other ways are gravity tracker, the ion shepherd, these are all ways of doing it. You don't need, it's very, very unlikely that you need a nuclear weapon. Now there's the idea of disintegrating with a nuclear weapon, and there's the idea of disintegrating with a gigaton hydrogen bomb. But it's very unlikely to happen that with such short notice that you need one of those, and we wouldn't have enough time to get it ready. And also the main problem is there is this proposal of using a gigaton that's twice the size of the Tsar bomber, which is the largest ones ever detonated. And so it's a practical thing to make, but there's a bit of a problem. They could make it would probably turn it into lots of smaller asteroids, and we need to know a lot about the composition of asteroids before we know whether that's a safe thing to do. Because suppose you made a few big ones, then you might be able to. So they came up with this plan for a gigaton one could vaporize 1 kilometer asteroid and deflect a large one. But then you need to be a bit careful about that. I mean, you need to have a very good idea about how the asteroid works. And perhaps an easier method is to, instead of impacting it, is to, and the largest nuclear weapon could be 10 gigatons. I think you call it a backyard weapon because you don't take it to the enemy, you just detonate in the backyard. It's easy exaggerating there, but these are very large. The other idea you see is that you can actually impact and detonate just above the surface, and then the blast of the nuclear weapon gives a bit of a shove, and that's one way. And it creates a bit of crater, but what it does is it shoves it and changes its position, and that might be a safer way to do it than just trying to split it up. You can also use solar-powered infrared lasers, and that's one way of doing it from orbit. But there's also breakthrough Starship. Now, if you were to collaborate, if we really wanted to have a working defense system to defend the Earth from long-period comets. So, yeah, the comets that come in with, we spot them maybe several years in advance. And this is the idea of, suppose we saw a 5 kilometer comet that was headed possibly for Earth, and you wouldn't know for sure at that distance because they keep moving because of the plumes of the tail of the comet makes it move around a bit. So if you saw a long period comet and even if you had this orbit very accurately, you still wouldn't know for sure if it was going to hit Earth or not, even if it was headed directly for us. But so you've got to deflect it by several times Earth's diameter for it to be worth doing. And they worked out with 5 kilometer asteroid comet, then you could, this is the proportion, this is if you've got an orbital laser, that's if it's on the ground at 20 degrees north, 25 degrees south, or if you did both of those, it's similar to the orbital laser. If you look at the orbital laser, then all of them can be deflected at least 5 Earth diameters, most of them by tens of Earth diameters. And you do that with just, you just deflect it with a few minutes a day. So the way this gigawatt laser works is that you store up the power all through the day, and then you just pulse it for 8 minutes, or something like that. And the laser, the infrared lasers, they just wouldn't even last for an entire day at that gigawatt, but they at 100 gigawatts. But you can pulse it for 8 minutes. It doesn't heat up too much. And if you had these, they want to do it for sending tiny solar sail spacecraft. They could get to Pluto in a few hours, and you could get to a nearby star in decades. And that's really why they want to do it. They want to send tiny spacecraft to nearby stars and hopefully find a way for them to communicate back. There is a potential way they could communicate back, even over that distance. Very, very sort of microgram, just a few grams spacecraft sent to a nearby star, and just with these pulses of infrared light, you could send it at up to maybe a tenth of the speed of light. So we could do it both at once, 100 gigawatt laser array, and I'm not sure what the cost is, but it's not trillions of dollars, it's billions of dollars. I'm not sure, I have to look up the cost, but this is something that we could feasibly build, but rather expensive, and it may be in a collaboration with these experts, and with these enthusiasts, not experts, who want to send, and some billionaires involved in the project, Breakthrough Starshot. And we could, with those together, have a defense system that we can use to deflect, and these are comets from arbitrary angles, and we could get all of them if we had one in the northern hemisphere and one in the southern hemisphere, and if we spot it, how many years in advance was it? 2 years in advance for 5 kilometer diameter comet. So and this is just my idea of my own, that I haven't seen it suggested by anyone. But could you do something? Maybe it's just so much easier to use the infrared ray, or other methods. But why not? Like the Apophis, send a space blanket, as it were, up to the comet and cover, say, one pole of it, because they have a north and a south pole, and you maybe want to deflect it south. So you cover the entire North Pole, or just a sufficiently large area, with this material that reflects the sunlight away, so you don't get any jets from one of the hemispheres. And because they found with Hale-Bopp that the probability of impact didn't reach 50% till the final 3 months, because of its unpredictable non-gravitational effects of its jets. And that Hale-Bopp is very massive, and so we're not likely to be hit by anything that big. The Earth hasn't been hit by anything that big, or even as big as Swift-Tuttle, for over 3 billion years. So these are incredibly rare that they come anywhere near Earth. But we could even deflect something that big. So it seems to me that could be a more effective way, especially if we ever, for instance, Swift-Tuttle has got a tiny, tiny chance. It's 1,000,000 to 1. It's expected to miss in 4479. It might be, but it's actually, Swift-Tuttle isn't very active, but and so maybe the jets wouldn't work so well, but it would still do something. And with Hale-Bopp, for a brand new one coming in, then the Hale-Bopp, yes, but even for a less active comet like Hyakutake, it was unpredictable right up to 20 days before impact. So this is just a suggestion. Could you just cover it with some material, and how much would you have to cover it with? And would this do? So I'm just suggesting solar cell material. So I took a, for instance, 10 kilometer diameter comet, then solar cell material, the mass needed to completely cover it, that would make it about 110 tons. And so maybe, you can sort of understand, and much less dense material. So maybe the starshot array is a more feasible way to do it than carrying such amounts of material up there. But anyway, if it was a really big comet, then we could do it that way in the future with better. Anyway, so I'll finish at this point, and that's my. So we can deflect them if need be. So let's just remind me. So, but remember, just put it in context. I'll just take it down to the did you know here. Just remind you that if the Egyptians had built an asteroid detection telescope back at the time of the Great Pyramid of Giza over 4,500 years ago, it would still be waiting for its first city-killer asteroid. And never in all of recorded human history, except there's one dubious Chinese account, which may very well be hailstones, where some people died of what could be either hailstones or fragments of a large asteroid, of a small asteroid that broke up. But apart from that rather dubious account, with very ancient Chinese history, then there's no historical evidence of anyone that actually any urban area being hit by an asteroid. And there have been individual people died, but it's extremely rare, and it's much your personal risk is absolutely tiny. And then we do expect to get asteroids from time to time. We certainly get more fireballs, big fireballs, and we can expect to get small asteroids, Splosh in the Pacific most likely, Splosh in the Atlantic and the other oceans, in Sahara deserts, quite a likely place, in the various deserts, in the ice sheets, Antarctica and so on. And then there's a very, very, very remote chance that anything even big enough to damage a city would actually hit a city. But we should watch out for them just in case. And that's why they're doing it. That's why they're looking for them. And then if we do find them, then it's just like hurricane warning. They're not going to just say, oh, we just noticed that asteroid is going to hit Miami. Don't tell anyone. Because we don't want to scare the people in Miami. Because they'll get very frightened if we tell them there's going to be an asteroid hits Miami. So don't tell anyone. Just pretend we haven't seen it. And then once they've all died, then we'll go around and we'll help all the injured people. I mean, governments don't think like that. Nobody thinks like that. Nobody's got a human soul and thinks like that. Who's got a heart, any kind of human heart to them, thinks like that. So, no, they're not hiding it. That's just a movie myth that makes for a nice story, but it doesn't work in real life.